Let's look into another method, which is LLaVa, and we are almost very close to finishing. So what you do is that you have a vision encoder, again frozen, pre-trained vision encoder. And in this case, so in the case of Flamingo, you have multiple layers. So you have cross attention for every transformer block in the language. Yeah? So you have one for every transformer block. For this LLaVa, what you do is that you have vision encoder and you have a one linear layer. That's it. And that one linear layer will bring the vision output into the language space. Okay, there is LLaVa 1.5 as well and LLaVa 2 as well, which shows that if you do two layers with one nonlinearity, it is better. Yeah. But doing some simple thing as one linear layer, so you have vision encoder, so you have vision input data token, so you tokenize, you have a vision output data token, you pass that through a linear layer, and that will bring you to HV space, which is actually language space. And this is your language model, LLM, which you froze. And what you do is that you do autoregressive training, and you only train this projection layer first. You freeze the vision encoder, you freeze the language encoder, you train this projection layer. And the purpose of this projection layer, or it can be one or two with one nonlinearity, doesn't matter much, is to bring the vision token into the language space. And then you pass it to the language, add the position embedding, so on and so forth, and then treat them as language token. That's it. Yeah? And then pass them through. So you pass that at the first layer of language, and they keep on interacting with throughout the language, throughout the LLM, and that does pretty good and decent job too. Yeah. Good. So this is one of the contribution which they have. The other contribution is the data set they have generated. So they have generated the prompting. So this is for visual prompting. Yeah. So you can do the chatting with this. So they use a prompting LLM which is called Vacuna. The previous Flamingo used Chinchilla, so they are using Vacuna model. So this is particularly geared towards chatting, interactive prompting and interaction with the chat with the vision language agent. Yeah. So for that they have designed the data set where they have given an image and answer corresponding to that image. So they have given the instruction and corresponding answers to train this model. And for every image they have multiple instruction and multiple answers. So they curated this data set. And another contribution is that they have taken 60 images or so, and they have described those 60 images in huge detail. So for example, they will describe where the strawberry is, where the blueberries are, where the milk bottle is, and they will describe it in very detailed thing. And they will describe the instructions corresponding to that, and this is used for evaluation. And they will benchmark different methods on this. So they have benchmarked Flamingo and so on and so forth, Blip and other. So what does this enable you? So this is an interesting image, and they want to see what is unusual about it, and this is what LLaVa is telling them. They can reset and they can ask that. So you can this is the capability which is coming from Vacuna, and they can ask you what is happening in this scene, and LLaVa is going to tell them what is happening in this scene. Okay, and this is the corresponding GPT-4, and this is Blip 2, and this is Open Flamingo. Open Flamingo is from Google, so they didn't open source it. Somebody implemented Flamingo. It's very straightforward, and they release it. And you can see that their response is much better. A man drying his clothes on the hood of this car, so that's Flamingo. And you can see that this is much better. Yeah, I will not go into detail, but you can see it's significantly better. It has better understanding. Let's look into the last method, which is CogVLM. Okay, and then we will conclude. So again, you have a vision model. So in this case, a fox is sitting next to books. Yeah, but okay. So the fox is sitting on the books. Okay, fine. So that's fine. So that's human annotation. The sample which is downloaded from the internet. Okay, there is a fox sitting on next to the books, and the caption corresponding is that fox sitting on the book. So you take the vision encoder and you take the word embedding. That's pretty standard. So this is your vision encoder. Typically these vision encoders are pre-trained using clip kind of losses. Yeah, but you can choose to train it using any of the losses, self-supervised learning, for example, Dino V2 or any other losses, and you can combine the encoders as well. You can send multiple encoders. That's not a problem either. So you have again MLP adopter in the same style as is the case for LLaVa. Okay, And then you add position embedding. You add rotatory position embedding. I will not go into detail of that. This is a specific kind of position embedding. Nevertheless, it is position embedding. Okay, and then you pass it through your vision language model. So this part here in dotted lines here. So this is your LLM, frozen, and this is your vision. So these tokens which are coming here are going to be image token, and they are also going to be text tokens. Yeah. So you pass it through the same layer normalization. So layer normalization is shared, and then after layer normalization, image token goes to image part, text token goes to text part, which is frozen. You do cross attention and so on and so forth. You inject it. So you do the projection. Yeah. So this is QKV projection. You do multi-head attention. Multi-head attention is fine because multi-head attention does not contain any parameters. Yeah, it's just the operation. After that, you pass it through feed forward network. So this is your feed forward network here, and there is a feed forward network for vision. So basically, what you are doing is that if there are 7 billion parameters for language, there will be 7 billion parameters for vision as well. Yeah. So you have 5 billion parameters for vision encoder, and you have 7 billion parameters for language, and in parallel you have 7 billion parameters for vision. So how it is trained? Using autoregressive loss. Language look into vision, vision never look into language. Yeah. So you always have the causal attention, and let's say that if this part is vision and this part is language, you will always do the autoregressive. Your language will always look into vision. You will not actually do any of, yeah. So that is as simple as that. And this enable us to do very interesting and fancy stuff, which we have already seen. So it has factual knowledge coming from LLM and vision input, and it can do some basic reasoning. For example, how many counting of the words. It can do a lot of other. It can help you with the recipes and things like that. It can do grounding as well.